Welcome everyone. On behalf of Forge College, I am absolutely thrilled to have you here for this explainer. We are anchoring ourselves right in the thick of the Foundations of Solidity syntax module, which is a key part of our Introduction to Solidity and Basic Syntax track on this Solidity from Zero journey. Now, if you were with us for our last lesson on working with variables and mutability, you already know the basic skeleton of a smart contract and how to change data around locally. But today we're tackling something much bigger. We're looking at how a smart contract actually remembers things permanently rather than waking up with a completely blank stare every single time it runs.
Here's our blueprint for today. We're going to cover the persistence problem, EVM storage and slot packing, modifiers, constants, and immutables, building the storage demo contract, and finally, verifying your storage layout.
So let's jump right into Part 1, the persistence problem, escaping contract amnesia.
We know how to mutate local variables inside a function, right? You do some math, you update a counter. But here's a very practical question. Where does your data actually sleep at night? If we don't save those variables to the contract level, our smart contract essentially wakes up with total amnesia the moment the transaction ends. Everything gets completely wiped clean. Variables declared inside a function without any permanent storage instructions, they just evaporate into the ether once the execution finishes. If you want your smart contract to remember, say, a user's balance, or who the owner is, or whether a flag has been triggered, well, those variables need a permanent home. They have to live outside the functions, right at the top level of the contract.
Which brings us to Part 2, EVM storage and slot packing, or, as I like to call it, 32-byte warehouse Tetris.
So what exactly is a storage slot? It's a discrete 32-byte space in the Ethereum virtual machine used to persistently store your contract-level state variables. I want you to think of these as exactly sized heavy-duty shipping containers sitting in a massive warehouse. Now, the EVM gives you a practically infinite number of them, but, and this is a big but, using them costs gas, which means it costs actual money. If you pack them poorly, you're essentially paying premium real estate prices for empty air.
Here is where the Tetris mechanic really comes in. Look at this breakdown. Large data types like a uint 256 or bytes 32 are bulky. They demand one full 32-byte storage container all to themselves. Even an address, which is 20 bytes, is going to take up a whole slot by default if it's just sitting alone. But smaller types, like a uint 128 or a simple boolean, they are much more accommodating. They actually don't mind sharing a slot at all, provided you declare them right next to each other in your code.
And that gives us the golden rule of storage. Declaration order matters for packing. Group your small types together to save gas. Seriously, if you declare a tiny boolean, then a giant uint 256, and then another tiny boolean, the EVM won't kindly rearrange them for you to save space. No way. It's going to put the first boolean in container 0, realize the uint 256 won't fit alongside it, so it shoves the uint 256 into container 1, and then puts the second boolean in container 2. You've just wasted 3 whole containers when you could have easily used 2.
Moving right along to Section 3, modifiers, constants, and immutables, the VIPs of the bytecode.
Now, some variables actually get to skip the warehouse entirely. Constant variables are placed directly into the bytecode at compile time. You'd use this for values that will absolutely never ever change, like a fixed maximum supply of a token. Immutable variables, on the other hand, are written at construction time. You set them exactly once during deployment, like maybe assigning the deployer as the owner, and then they get permanently embedded. Because these VIPs are stamped directly into the building's foundation, they don't consume standard, expensive storage slots at runtime at all.
We also really need to talk about visibility for a second. When you declare a state variable as public, Solidity does you a massive favor and creates an automatic getter function so anyone can easily read its value. If you mark it private, well, it hides it from other external smart contracts. But please, never forget this absolute golden rule. Private does not mean confidential. Anyone, anywhere, can still inspect that storage slot off-chain because the blockchain itself is entirely transparent. So please, don't go hiding passwords or secret keys in private variables.
All right, Part 4, building the storage demo contract, drafting the blueprint.
Let's actually put this into practice by drafting our blueprint. First, we place our declarations directly inside the contract body, totally outside of any functions. We declare a uint28 public small number, and immediately underneath it, we declare a bool public flag. Now, since the boolean is small, it happily shares slot 0 with our uint28. They pack perfectly together. Then, we declare an address public owner, which is too big to fit in the remaining space of slot 0, so it proudly takes up the entirety of slot 1. Oh, and as a crucial best practice here, always add explanatory comments detailing your storage intent. Just write down exactly which slot you expect these to end up in.
Finally, Section 5, verifying your storage layout, inspecting the warehouse. Because we're engineers, we can't just cross our fingers and trust that our packing worked. We have to actually verify the layout. Here are the exact steps. Step 1. Create your StorageDemo.sol file with those top-level state declarations we just mapped out. Step 2. Compile it. You can do this locally using hardhat by typing npx hardhat compile in your terminal, or you can just pop it right into the online Remix IDE and hit compile. Step 3. Inspect the auto-generated application binary interface, or ABI. You just want to confirm that those public getter functions actually exist. Follow this process, and if compilation fails, it's time to put on your detective hat and hunt down those missing semicolons.
Let's do a quick recap of our engineering blueprint today. First, you absolutely must declare variables at the contract level if you want them to persist. Second, you are now officially a warehouse Tetris master. Group your small types together to pack slots and save gas. Third, marking variables as public generates those handy getters, while using constant or immutable lets you bypass the standard expensive storage slots altogether. And lastly, always verify your layout by compiling and checking the ABI.
So, I'll leave you with this final thought. Your variables are safely stored in their designated containers today. They have a permanent home. But how will you securely mutate them tomorrow? How do we build the machinery to interact with this warehouse safely? Well, to find out, we're going to wrap up this Forge College explainer here. Head over to forge.college to dive deeper and prepare for our next lesson, where we'll be defining and invoking simple routines. Keep building, keep learning, and I'll catch you in the next one.